Alright, so although my roommates are here, I'm still going to record it anyway. Start. Oh god, I should really switch off the net. Better. Alright, just start. So, exercise 3, here we go. In how many ways can 2 n people be seated in at a round table and in a row? For instance, okay, cool. And in a round table, and just select these n people anyway. Just that's like 2npn. Okay, so just 2np. What am I writing here? 2npn, and plus the remaining n people you want to sit them in a round table, right? That's like n factorial ways upon n. So just minus 1 factorial ways of doing that exactly. Does it matter where the seats are in our? I don't think that does. It's just their order that matters, right? Hopefully. Yeah, hopefully. Around. So yeah, are the seats actually fixed at the place, or can we just keep rotating and still consider the same? I mean, I think we can rotate and still it's still the same. Yeah, that's how it should be. Okay, then this is the thing. Of course, let's just do this thing. 2n factorial upon n factorial. That's this thing. Plus. Wait, so what kind of question? It's subjective. Are you serious? The whole exercise 3 is subjective? God. Oh no. Fine, no big deal. You can still write it down. Okay, what's happening to the table? Next question. This is 2npn plus minus 1 factorial. Next question. And since they didn't give us any value of n, just leave it like that. Find the number of selections of 5 cards from a pack such that all 4 suits are present. Right? All 4 suits. The 5th one, we don't know which suit it's gonna go in. Okay, so one suit is repeated. That's all you're saying, right? So 4 ways of figuring out which suit is going to be repeated, and then you just want to choose, right? Exactly. So in each way we are talking about, first you want to choose 2 from a single suit. That's going to be 13c2 ways of doing that. Well, that times, so yeah, from each of the other ones it's just 13 13 13. That makes sense. It's just 13 cube, and this is going to happen. Yes, so it's 4 ways of doing that. That makes sense. This is our answer. Now it's actually calculatable. That's nice, but I won't calculate it because 13 cube, who even wants to calculate that? Okay, fine, just continue. So this is 4 times 13 times 12 upon 2. I guess it's just 6 over there. So it's 24 times 13 power 4, which I won't calculate. I mean, why would I even calculate that? Alright, cool. Next question. Third question is, there are 70 people including A and B. In how many ways can 12 of them be chosen if both A and B are not chosen together? 70 people including A and B, 12 of them are to be chosen if both A and B are not chosen together. So first you can just find, well actually that's not quite correct. You can break that, right? So first we'll just say none of A and B are chosen, right? Then there's like only 15 people, so just 15c12. Then we can go with only A is chosen, and necessarily A is chosen, so that one guy is already there. So now there's still 15 people, but now from that you want to choose 11 people. So got 15c11. Actually it's going to be 2 times of that because, yeah, right, 15c11. And then finally just want if, yeah, so if wait, you don't want them to be chosen together, right? Exactly. So just we just won't count that stuff. Fine. So that's the number of ways that you can choose 12 people. And yeah, I mean, I guess that was the thing. So 15c12, yeah, if you're not using A and B, then if you're choosing one of them, right? Sure, that should do it. Okay, cool. Which is like what? It's the same thing as 15c3. This is 15c4. So just get 15 times 14 times 13 upon 3 times 2, I guess. Yeah, this would be just 5 over there. This is going to be 7. So 5 times 7 times 13. plus 2 times of this stuff, which is, well, let's just calculate 15 times 14 times 13 times, hey, we already got 15c 3, right? So just for 4 it's gonna be this times 12 upon, well, 4, what else, like 4 factorial, of course, is 3. So the same stuff as this thing, 5 times 7 times 13, but that times 3. I guess that makes sense. Sure, it makes sense. Okay, that's our answer. Just take this common, 5 times 7 times 13, and then you got what, 2 times of h is 6 plus 1 is 7, so this is the thing, right, which is like what, 49 times 5 times 13, something like that. It's fine. Okay, just 65, that should be the thing. This is like this times 50, which is 3250. Yeah, that's the thing. Okay, minus 1, which is just this minus 65. I should probably do it. Yeah, definitely. I'm going wrong somewhere. No, it's correct. Okay, just 5, and you got 4, so it's just 8, 1, 3, 1, 8, 5. Next question. So yeah, finally a question which you can usually calculate, and we don't have to give completely subjective answer like the first one. Next, fourth, how many ways can 3 distinct numbers be chosen from 1 to 30 so that their sum is even? Okay, 1 to 30, you want to choose 3 distinct numbers, their sum should be even. How many ways can that actually happen? So let's start all of them odd. That's one thing. So just odd. Yeah, that sure happens. Wait, the sum is even. That's not gonna work. Sorry, what am I doing? So you can have all even numbers, that's gonna work definitely. Then let's go to 2 even numbers. Can that work? No. Then only a single even number, that's gonna work. So all even, then you got 1 even, 2 odd, that's gonna work. And last one would be 0 evens, all odds, it doesn't work. So these are the only 2 ways. Alright, so 3 distinct numbers. Let's just go with even numbers first. So you're gonna have like 1 to 30, 2 to 30 basically. So that's actually just split, right? Yeah, every next one is going to be an even number, so just split in half. 15 even numbers over there, so just 15c3 for the first guy, and for the second guy you want 1 even number, so for just 15c1 from there, and then odd numbers. So from the other from the other set, other 15, just want to choose 2 numbers. That should do it. So that way you consider that set, and yeah, those are the number of ways. Cool. Which is 15 times 14 times 13 upon 3 times 2. That should be the thing, which is 5 over there. We already did this, right? Yeah, we already did this. 5 times 7 times 13, and this one is just plus 15 times 15c2 is like 15 times 14 upon 2, which is 15 times 7. Nice. So let's take some stuff common. Actually, we can take 7 common at least, and 5 common. So 5 times 7, which is 35. Take that common. What do you get? Just get 13 plus you got 3 times 15 times, well, that's gone, so just 3 times 15, which is just 45. So this is going to be 58 times 35. You have to do the calculation. Well, this is stupid. Or you could just split this in half, and yeah, it's like 7 times that. It's just going to be 10 times split in half. 25 3, just 25 4, 29. That's the thing. Sure. Which is so like 14 and 63, I guess. Yeah, just 2030. That's our answer. Hey, 2030. That's like, okay, whatever. I mean, if this was going to be in 2030, right? JNet was 2030, that would be awesome. Anyway, next question. Is this correct? I'm not gonna check that actually. Just move on, because this is personal practice. I'm not solving it for some exam. Okay, fifth. How many ways can 27 distinct books be distributed among A, B, C so that C gets half as much as A and B together? 27 distinct books distributed among 3 people. Okay. Third gets half as many as A and B together. Exactly half. So yeah, okay, cool. Yeah, I mean, that's not a big deal. A and B together. And then you want to distribute. Oh, all right. That's actually gonna have multiple ways of doing that. Right. So each of them is actually gonna have 2 ways. So can it be that A does not get anything, so is 0 allowed? So what's gonna happen is that for C, if you got like X books, which will select, I don't know, and then over here you got 2 X books for A and B combined, then each of these 2 X books has like 2 choices. It can go to A or B. So yeah, it's like 2 power 2x, and then for these x, I mean those are already there. Okay, cool. uh, and then that time, so you just want number of ways that you can actually choose this thing, right? Kind of like that. So first you want to choose these x books, right? uh, from how many books was there? 27 books. 27 cx, and then from the remaining stuff, which is 27 minus x, you want to choose 2x books. Why does it look familiar? No idea why does this look familiar though. Yeah, exactly half, that's the thing. Or you can just choose 3x, and then from the 3x you can choose the x, right? I mean, that's pretty much the same stuff, isn't it? So it's like 27 c3x, then you got 3x c2x. This should be this should be the same as that, it seems. What's this like? It's just 27 factorial. Yeah, just actually calculate this first, because maybe it is the same. 27 factorial upon 3x factorial. Okay, then you got 27. Where's the 3x over here? I don't get it. Oh, okay, it's gonna come. Actually, it's gonna come. 27 minus 3x. Okay, factorial. Then this is 3x factorial. Once right, it cancels as expected, and then upon 2x factorial and just x factorial. So it's just 27 factorial upon 2x. It's multinomial. Okay, understood, fine. So then, yeah, you're not choosing, actually. It's what is it that you're doing? Oh, you're actually making 3 kind of sets of this, right? So the first set, which needs 2x, and then the next one needs x, and the next one, right? Okay, you're actually making sets of this. Well, that makes sense. So the basic rule stays the same. Just first of all, arrange then divide by the number of ways you can arrange in these sets alone, right? And that's why it's going to be 27 factorial. So this combined is just 27 factorial, and then upon 2x factorial, because 2x things over here, then x factorial, x things over here, and then 27 minus 3x over there. Oh, so this was actually pretty obvious. We didn't have to do all of this to get that. So this multinomial coefficient, and that times 2 power whatever this thing is, or just 2 power 2x, sure. Yeah, so this is the thing, but then you want to, yeah, this is like a summation in x, isn't it? So isn't there some better way to be doing this other than just summing stuff up? Why is there a multinomial coefficient, 2 power 2x? Like, I've seen that somewhere, haven't I? So yeah, there's gotta be some other way. Why is it just exactly half of that? Come on. Maybe the summation will give us something nice. So just 27 factorial upon, actually is replace x by r. So just 2 power 2r. We got 2r factorial over there. You know what, actually write this like 4r instead. 4 power r. Okay, this is like r factorial resonance, r factorial. Okay, and the summation of this thing is r goes from what? It start off at 1, right? Yeah, so you need at least 1 book over here. What if there's like 0 books? Nah, that's not gonna work. You start off at 1, because there's, and this would also be 0 books. And then wait, but that's also a way to do that, right? Distribute innocent books among these. Wait, so do we have to distribute all the books, or is it like only a subset of these 27 books? How many ways can 27? Oh, right, so we don't have to sum. Okay, that makes sense. Fine, this thing has to be 0. Okay, cool. Yeah, so x has to be equal to 9. That's it. You have to provide all the books to these people. You can't leave any book, it seems. Well, that's just that the question is vague. They didn't actually tell us how are we distributing the books. Do we have to distribute completely or not, or what, right? Anyway, So if it is like we have to actually distribute completely, there's no third thing, and x is equal to 9, so you just get like 27 factorial, basically like 27c 9, right? Because this is gone, 0 factorial. This thing is just 9 factorial, this thing is 18 factorial, so of course it's just 27c 9. Okay, let's just start. This is going to be hard to calculate, or why even calculate? It's just subjective anyway, right? Awesome. Yeah, that's the number of ways of doing it, seems. Oh, that times the 2 powers of, right, so that times of 2 power 2s, which is like 18 exactly. So this times 2 power 18, this should be the thing. Awesome. Sixth question. Okay, 20 lines are drawn in plane, no 2 lines are parallel and no 3 are concurrent, so that they divide the plane into 2 1 disjoint parts. So what is it given? No 2 are parallel. Awesome. So this I have seen it before, right? So let's just say that you have like n lines in the plane, right? And a of n is the number of regions that the plane is divided into because of these n lines. Then when you add another line, then it's gonna intersect all these n lines exactly once, right? Yeah, and so there will be like n intersections that you have, right? And there will be 2 open ends. So in that way, number of line segments that you generated, those will be n minus 1, right? So you got n minus 1 line segments. I mean, think about it, just this line, and then there are, so let's just say for n equal to 3, you had 3 lines already. We don't care where they intersect, but yeah, just draw another line. You got 3 intersection points, right? Pretty obvious. Then there are like 2 n minus 1 line segments, and then plus 2 rays like this. So thing is, every such line segment or ray splits some region into 2 regions, so it actually adds a region, right? So here this was one region, you split that into 2 regions, basically you're adding another region. So these are the number of regions that is added. So you can say like an plus 1 is equal to an plus n plus 1, right? Exactly. So from here it's pretty easy to see just some kind of summation. Okay, what's a1? A1 is, so if there's only like one line, it's going to be 2. Then a2, that's going to be this thing, 2 plus 2, because over here you got n plus 1, this is n plus 1 as well, so just 2 plus 2 is 4. Then a3, yeah, you get the thing, right? So a1, you can think of it like 1 plus 1, so that 1 was there by default, right? So a0 is 1. Yeah, awesome. So a0 is not 0, it's actually 1. So you know, an, that's actually going to be, this 1 is always there, and then you just got, because of 1 then 2, then yeah, so just 1 plus 2 plus 3 till n. So this is just 1 plus n times n plus 1 upon 2. Yep, that's the thing. Awesome. That's what number of regions will be because of n lines, which are, none of which are like concurrent, 3 of each concurrent, and they are not parallel, any of them. Then it's gonna be just exactly 1 plus n times n plus 1 upon 2 regions, of course. So in this case, it's 20 lines are drawn, and sure, so n equal to 20, just get 1 plus 20 upon 2, like 10 times of, well, that's like 11, so no, 21, so just 210 and plus 1, this is 211. That's the thing, 211 regions, that's what we get. Next question, we just had to show that, right? Actually, I'm just gonna give the formula. So the sixth one, regions, because of n lines, that's going to be 1 plus n times n plus 1 upon 2. Or if you want to go fancy, you can just write like n plus 1 c2. Next question, 7th. How many ways can a 12-step staircase be climbed? This is actually a nice thing. It's involving Fibonacci sequence of, so the funny thing is I'm doing this because I want to get practice, but then I've already solved these kind of questions. So this is not giving me that much of practice as it gave the first time I solved it. Well, but anyway, let's solve this. How many ways can a 12-step staircase be climbed, taking 1 step or 2 steps at a time? So let's forget it's a 12-step staircase. Let's think of it as an n-step staircase, and the number of ways of doing that is a of n. Then right, so first, if you just take 1 step, then you have to take n minus 1 more steps in total, right? So that's like an minus 1 basically, right? But then you could also have took 2 steps at the same time instead of taking that 1 step. So then you have to like cross n minus 2 steps in the same way, taking 1 step or 2 steps at a time. So then that's just an minus 2. So basically just Fibonacci sequence. Not exactly, because it start off at a different thing. So a1 is just 1. There's only one way you can do it. Take a single step. There you go. Yeah, a2 you can do it in 2 ways. You can take two single steps or 2 step. This is weird, but yeah, that's the way I'm gonna do it. So from here you can generate the whole sequence. a3 is just the sum of these two, which is like 3, and a4 is 5, and so on. Okay, so what do you want? You want 12 steps staircase. So you want a12. Oh god, that's hard, isn't it? Oof. I mean, sure, we can generate a binomial sequence for Fibonacci. Yeah, we can actually do that, right? So I've already done that once. It's gonna take some time, but we'll get it done. Okay, so let's do this. What's the characteristic polynomial equation for this sequence? Is r squared is equal to r plus 1, right? So then this guy's having this equation. This guy's roots are minus b, just 1 plus minus square root of b squared, just 1 minus 4ac, like that's 5 upon 2. Okay, cool. So just get like 1 plus square root of 5 upon 2 to the power of n times some number a plus b times 1 minus square root of 5 upon 2 to the power of n, right? That's what our sequence is going to be. That is our an. And now our problem is to figure out what a and b should be. So yeah, I mean, all of this is actually just assumption. We are assuming, actually I should not be using a again, it should be alpha or something like that, because we already used a once. Okay, so let's just start putting stuff. So we'll put n equal to 1 in there, right? Or you could put 0. So I mean, actually that doesn't quite make sense, but you can already see what kind of thing is going on, right? So assuming this also goes on for 0 and stuff, you can actually figure out what this should be, because this is equal to this plus that, so this is just this minus this, which is 1. So we can start putting n equal to 0 in there. So you just get like alpha plus beta, that's equal to 1, and then you can put n equal to 1. So then what you get is like alpha plus beta upon 2, which is 1 upon 2. So 1 upon 2 plus square root of 5 upon 2 times alpha minus beta, right? That is equal to also 1. So this is just 1 upon 2 over there. Then multiply by 2, just get this thing. Alpha minus beta is equal to 1 upon square root of 5. That's what you get. And then alpha is just 1 plus 1 upon square root of 5 upon 2, which is like square root of 5 plus 1 upon 2 square root of 5. So putting that over there, oh, this is actually nice. That upon 2 also is included, so just n plus 1, but then you have to put 1 upon square root of 5 over there. What about beta? Subtract, just get like 1 minus 1 upon, yeah, so just 1 minus 1 upon square root of 5, and that upon 2. So this is like square root of 5 minus 1 upon 2, which is negative of what it's inside. Okay, just put negative over there. And there's the 1 upon square root of 5 over there as well, so just this thing plus 1. Awesome. So that's our sequence, but this is actually quite useless because you don't know how to calculate like powers of irrational numbers and stuff. So you know what, I'm gonna do something else. I'm gonna binomial expand this. Yeah, right. So this is n plus 1. You know what, actually just go with an minus 1 instead, just to get a better thing. So an minus 1, and I need more space. Okay, so an minus 1 is going to be 1 upon square root of 5 times, you know what, actually take that 2 power n over here as well. So yeah, this is the thing, and this times of 1 plus square root of 5 to the power of n minus 1 minus square root of 5 to the power of n. So expand this, it's just like nc0 square root of 5 power 0 plus nc1 square root of 5 power 1 plus nc2 square root of 5 power 2, so on, and subtract from that. sorry for that. Okay, subtract NC0 square root of 5 power negative square root of 5 power 0, and then it's like alternate negative positive because of that negative over there. Alright, plus NC2 square root of 5 power 2, and so on. So then when you subtract this, well, this cancels, which is like 2 times of NC1 square root of 5. And the next one is going to be plus NC3 square root of 5 power 3, which is like square root of 5 times 5, then plus NC5 square root of 5 times 5 squared, right? That makes sense. Okay, well, there we can just use this square root of 5 and cancel all of this stuff away, and also use this to make it 2 power n minus 1. So just got like 1 upon 2 power n minus 1 over there, and this stuff is just NC1 plus NC3 times 5 plus NC5 times 5 squared. Looks familiar, doesn't it? Exactly. And just keep going. So we don't know where we will stop actually. Yeah, that looks like that should be the thing actually. It's still weird, 65 over there, but that's the way it is. So you have something that we can actually now calculate. So this is the thing. It's NC1 plus NC3 5 plus NC5 5 squared, so on, right? And that upon 2 power n minus 1. Awesome. That's what a minus 1 is. Okay, so what do you want to do? You want to calculate, actually, why you want to do all of this then? Just delete this stuff. And there you go, you got the general term of our sequence. In this particular case, you want 12 step staircase, so our n minus 1 should be 12, so n is equal to 13. So you just start like 13c1 plus 13c3 times 5 plus 13c5 times 5 squared plus 13c7 times 5. Have I seen something like this anywhere? No, not really. Just the odd numbers, right? No, I've never seen that before. I mean, I have seen that one relation between some kind of series involving dynamic coefficients and the Fibonacci sequence. I don't quite remember. I mean, I made a video on that, right? I've already done all of this once before, so I know that there's something like that. But yeah, whatever, just continue. So it's 5 cubed, right? Yeah, plus 13c9 5 power 4. Man, this is still very inefficient, isn't it? Isn't there some better way of doing it? Like, is this 2 power something? It could be. Yeah, it sure could be. And I definitely don't want to be calculating 13c5. You could just use Pascal's triangle. Well, actually, that's also stupid because, yeah, you definitely don't want to be doing that. Whoa. This is kind of weird. Now what? Right. Oh shit, this is messed up, isn't it? Now what do I do? I don't want to be calculating all of this. Maybe the recursion way is the better way, right? I hate to say it, but yeah, the recursion is actually better. So this is good if you want to put this in a computer program, but not if you want to calculate it by yourself. So you just have to do the recursion anyway. Why did I even do all of this if this is not going to be helpful? Well, anyway, so let's just start. A0 is equal to 1, A1 is equal to 1, A2 is equal to 2, actually just put this 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, we don't need 13 actually, just need 12. So then, just 1 plus 2 is like 3, this is 5, this thing is 8, this thing is 13, you got 21, 34, 55, this is 3, right? Yeah, just 89, 4, 1 carried on, you got 6, 1, 4, 4, and finally just 3, 1 carried on, you got 5, just 3 once again, 2, 3, 3, that's our answer. Yeah. We did too much of work really. It's just 2 3 3. That was easy. Should have done it the, the basic way the first time itself. So 2 3 3 is our answer. And we also got a formula which we can put in a computer program. Okay, 8th. Each side of an equal triangle is divided into 6 equal parts. The corresponding points of subdivision are joined. Find the number of equilateral triangles on it the same way as triangle ABC. Okay, 6 equal parts. The corresponding points of subdivision are joined. Corresponding points. What does that actually mean? Each side is divided into 6 equal parts. The corresponding points of subdivision. Number of equal triangles oriented the same way as triangle ABC. Oh, I see what's happening. So first we should just draw this, because who knows. And then you have to divide it. Actually, let's not start with 6 equal parts. Let's start with something easier to handle. Let's just say 3 parts. Okay, then they are saying the corresponding points of subdivision are joined. So this will be joined with this, which will be joined with this. So that's one equilateral triangle, and then you want it to be this. Yeah, the orientation should be the same as that, huh? Okay. How is that ever going to happen? I don't think we will ever get the same orientation. No, we won't. Yeah, actually you won't get the same, you will never get the same orientation. So like, let's forget about this completely and just, just think about what exactly is going on. See, so it doesn't even matter if these are like some special points. Let's just think of a random point, right? So if this is x, this complete things like 1 minus x, whatever. This is x over there and this is x over here. You join this and then you can actually visually see. I mean, come on, does this look like it's ever going to be the same orientation as this triangle? No, right? It will never be. Corresponding points of subdivision are joined. It doesn't make sense. It just doesn't make sense. It will never be the same orientation. Yeah, 0. That's the answer. Without thinking, we can just say it's gonna be 0 because of the word corresponding. So if this was not corresponding, then maybe there would be some kind of problems, but no, this way it has to be 0. Come on. Yeah, doesn't matter where x is. As you move this, when are you even going to get the same orientation? You will never. You'll get the opposite orientation, sure, but no, the same orientation just not going to ever happen. Exactly. Unless x approaches 0 and then it's almost the same orientation. Or if x approaches 1, then it's almost the same orientation. Otherwise you will only get, so if this is 0, then this side is like this, and as it goes over here, so when it's in the middle, this goes like that, and over here it goes like this. So yeah, it can only achieve the opposite orientation. It will never get same orientation, really, never. Yep, that's just how it is. Okay, next question. Right. Let n be equal to 10 power 6. Evaluate the summation. D divides n log base 10 of d. So it's like log base 10 product of d divides n. Okay, so the product of all divisors of n, you're saying, right? Sure. So it's 10 power, okay, it's a perfect square, huh? So other than 10 power 3, all other divisors will be in pairs, right? That is, they will multiply with their pair to give n. Right, so take that 10 power 3 away, and then you're just gonna have, well, first of all, how many divisors are there? It's 2 power 6 times 5 power 6, right? So there's 49 divisors. Take that one divisor away, all the other 48 divisors, they will in pairs, so you will get 24. um, what 10 power 6 basically. So yeah, 10 power 6, the power of 24, and then the last one is just in power 3 versus square root. Awesome. And this is inside log base 10. Sure. So this is 3 plus 6 times 24, which is 12, and then 24 is like 144, which is 147. Yeah, 147 is one answer. Next question. 10th. 10th is how many arrangements of 9 letters these letters are there such that y is between x and z. Any two or all three of the letters x, y, z may not be consecutive. So that's like a restriction. Fine. Wait, is this a restriction or it's saying that that's not a restriction? Wait, what? It says it may not be consecutive. It's not like it must not be consecutive. So then, yeah, it's basically saying like, okay, it's allowed, but not that it's necessary. Is that how it should be interpreted? I guess so. Fine. So it just has to be between x, y, and okay, then that's actually pretty easy. Just put x, y, z like this. You want y to be between x and z, right? And then start inserting stuff. Exactly. Or you know what? Actually, don't even do that. Take that x, y, z away. You got 1, 2, 3, 4, 5, 6 other characters. Just form a string of those characters, which can be done in 6 factorial ways. And then yeah, just start inserting things inside. So first you just insert x. You will choose a position to do that. Okay, this is actually kind of weird. Yeah. This is really weird, isn't it? I see. Oh, so the thing is, you don't want this to be 6 factorial. Instead, you want to leave spaces. So 3 spaces should be there. So let's just start with the first one, A. So A will actually have 9 ways, 9 places to go to. So really it's like 9 times 8 times 7 all the way till for all these 6 characters, right? So the last 3 to 1 there remaining just only 4 over there. So these are 6. I guess that's the case. Yes. Okay. And then for the last 3 spaces which are left, you just want to put x, y, z in that order. So it's only one way we can do that, not 3 factorial ways. So yeah, this is the thing. Isn't this like 9p? Huh, that's weird. So it is just 9p6. 9 spaces permuted in 6. Wait, what? Whatever, just one. Yeah, it's still weird. Usually the way this would work is like putting 9 spaces. Oh, okay, so the spaces are like numbered, assume that. So then you're putting numbers into this string. And this only a string of 6 characters because these 3 we won't put that, we'll decide at last. That's why it's 9p6. Okay, that makes a lot of sense. Cool. So there we go, 9p6. That's our answer. Next question. 11th. From amongst 8 married couples, a team is to be selected for a mixed double match. Find out the number of teams in which spouses are not included. Okay, 8 married couples. The number of teams in which spouses are not included. So if you are selecting it, you cannot actually select it. Right, so it's like a choice if you want to select the male spouse or the female spouse. Right? Exactly. Fine. So 8 married couples, right? From these you want what? A team is to select for mixed doubles match. Wait, what? Okay, you just want to choose 2 couples in that case, and then from those 2 couples just either male or female, like that. Is that the case? and the spouses are not included. Yeah, a team is only of two people in this case because it's doubles match. Fine, so then it's pretty easy, just 8c2, and that times of 2 power, how many doubles were there? 2 again. Yeah, that should be it. So just 8 times 7 upon 2 times 4. I guess that's the case. Exactly. So 16 times 7, which is 742. Exactly. Okay, just 112. Next question. 12th. 12th is n equal to this thing, find number of positive integral divisors of n squared which do not divide n. Positive integral divisors which, wait, what? Do not divide n. Oh, okay. They divide n squared, but they do not divide n. Fine. Understood. So like, first of all, prime factorize n. What do you get? It's like 2 times 5 times 18, which is just 2 times 9. So 2 squared times 5 times 9. Okay, that's n. You want, okay, number of positive integral divisors which do not divide n but are divisors of n squared. Why does it look like I've seen this somewhere? If that does not divide n, well, whatever. So n, this is n, and n squared is 2 power 4 times 5 squared times 9 power 2. So let's just say that our divisor that divides n squared but not n is like 2 power x times 5 power y times 9 power z. Then what should happen is that x should be between, so it's not actually even supposed to be equal to 2, because if it was, wait, no, it's more like 1 of x, y, or z must be between, it should be like bigger than 2 and less than 4. Either this or y is, wait, why can't we just figure out the number of divisors of n squared and then subtract from that the number of divisors? That should be the thing. Why am I even doing all of this? Yeah, that's just how it is. Why even go through all of this logic? So right, this is our n. Number of divisors is going to be 3 times 2 times 2. For n squared is just 2 power 4 times 5 squared times 9 squared. So the divisors are, oh shit, it should be 3 squared over there. It's not, 9 is not a prime number. So then this would be just 3, and then here's 3 power 4. So then the divisors of n squared, those are 5 times 3 times 5. So subtract that from that. Yeah, number of divisors of n are subtracted, so we're not counting those divisors. That's it. That's all the logic we need. Okay, cool. Just calculate things like 3 times 25, which is 75. 75 minus 9 times 2 is 18. Minus, what am I doing? Okay, so 15 minus 8 is just 7. You got 6. 6 minus 1 is 5. Well, yeah, sure. 57. Next question. 13th. How many arrangements of this letter, Mrs. whatever, have no consecutive s? No consecutive s's. Okay. Right, the same thing. Just first of all, M I I P P. Just how many are there? It's like, okay, 1 M, 2, no, yeah, okay, 2 P's, and 1 2 3 4 4 I's, and then 1 2 3 4 4 S's as well. That's what this thing is. So these characters, you want to arrange them basically, right? Yeah, that looks like the thing. So how would you do that once again? Oh, it's almost yeah, it's very similar to how you arrange. Well, okay, so I get it. First, just 1 plus 2 plus 4, which is 7 factorial upon 1 factorial, 2 factorial, 4 factorial. That's it. Huh. Easy as that. So that's number of, what do we call it, arrangements of these strings. Now we want to insert s in there. So there are 7 of these guys. So 8 spaces where you can insert s. Exactly. So just 8c4. There we go. That should do it. This looks awesome. With no consecutive s. There we go. Problem solved. 1 factorial is 1. So this is like 7 times 6c2 times 8c4. Is that correct? Looks correct at least. So 7 times 6 times 5 upon 2 times 8, 7, 6, 5 upon 4, 3, 2, 1. Okay, this cancels. This cancels. So what do you get? You get like 7 times 6 times 5 times 7 times, that's gone. It's just 5 once again. Sure. Which is like 7 times 3 times 10 times 7 times 5. I guess that's correct. Yeah, I hope that is correct. That's the extra 5n. Cool. Let's just calculate this thing. Sure, it's just 8c4, and that's the binomial coefficient, multinomial coefficient. Cool. Okay. So what's this going to be? Just 49 times 3, which is 12, and then you got 27. 27. Yes. 147 times 5. Oh no. Times 10. Yeah, sure. So just 5, 3 carried on, it's like 70. 7350. That's our answer, 7350. Next. 14th is find the number of ways of keeping two identical kings on 8 into 8 chessboard so that they are not in adjacent squares. Two squares are adjacent when they have a common side. Two identical kings on an 8 by 8 chessboard so that they are not in the adjacent squares. Fine. Okay. Oh, so the border ones are actually more complicated, isn't it? Yeah. I just want to choose two of these guys. Okay, so what are the things that will decide these places? The xy coordinates, of course, right? So let's just think about x coordinates first. Oh no, okay, it could be yeah, it could happen that the x coordinates are the same and then the y coordinates are okay. This is kind of weird. And the y coordinate could be anything. Oh, why not just do it like this? All the ways that you can actually do this, right? So there's 64 places. Just choose two of these places. So 64 C2. Subtract from that number of ways, and then these in which they would be in this adjacent places. So if they're in adjacent places, the formation could be like it's right next to it or it's right above it, right? So the ways to arrange this is like in how many ways? Your y coordinate can have like 8 places, and your x coordinate for this one is only 7 places. Similarly this, except it's rotated, so yeah, 8 times 7 still. So 2 times of this guy. It makes sense. Sure. So just 2 times of 8 times 7. Yeah, that's the thing. That's the number of ways. That's the number of ways you can actually do this, I guess. Yeah. 64 times 63 upon 2 is just, oh, it's gonna be hard. It's gonna be hard, definitely. Let's say 8 times 7. Okay, let's just take some stuff common. You can take 16 common. 16 times, well, this is 2 times of this guy, just 126 minus 7. Is that right? Hopefully. This is 119. Oh god. Just like 7. 1904. Next question. 15th. See, it's not that bad. Actually, I'm getting back into it. A coin is tossed 10 times number of outcomes in which two heads are not successive. Oh, very similar. Okay, fine. Two heads are not successive. It's 10 of these guys. Oh, wait. Some kind of recursion or something? Yeah, we can actually build a recursion from this, can't we? Right. So a of n, that's equal to, first if it's heads, right? It's not successive. That's the thing. Actually, kind of weird. You just like start inserting heads. You can't insert heads if you don't know how many heads are to be inserted, and you don't want this to be summation. You just go with the recursion thing. So an is equal to a so first if you put a tail, then the next one can be anything, it doesn't even matter, right? So just n minus 1. And if you put a head, then instead the next one has to be a tail. So then for the n minus 2 that are remaining, you can have anything starting, right? So yeah, okay, once again a Fibonacci sequence, and this time it is the Fibonacci sequence, not like, yeah, that is the recursion really. Exactly, this is a recursion, sure. You cannot have adjacent heads. Fine. This is weird though. And the coin is tossed 10 times. Okay. So you want a10, right? What's what's a0? Okay, that's actually stupid. What's a1? You can either have a head or a tail, so those two ways. What about a2? So if the starting one is a head, then next one can be a tail only. You cannot have two heads, so that's one way. Then you can have a tail and a head, that's also possible. And you can have both tails, that's also possible. So there's only three ways of doing that. Starting to make sense, huh? Yeah, sure. And now just keep going. So it's just a Fibonacci sequence, and you want a 10, right? Okay, so for 3 it's going to be 5, for 4 it's going to be 8, 5 it's 13, 6 it's 21. Haven't we done this already before? Yeah, I guess we have. Why is it selecting stuff that I don't want it to select? Okay, for 7 it will be 34, for 8 this is 55, 9 that's 9 and 8 over there, for 10 so we 4, 1 carried on, so 6 is like 1 4 4. Wait, did I mess up somewhere? We didn't get this last time, did we? 55. No, I guess we did actually get this. 1 4 7, that's what we got, right? No, something's wrong. Something has to be wrong. Where's that one? Okay, that's actually a different thing altogether. Where's the Fibonacci guy thing? Oh yeah, this one. So 7th. So it was 12, right? Except this was different in that a1 was 1. Which is like shifted. Fine. In this case, the thing that we'll be looking for is like a13. So that would be 2 3 3, it seems. Just keep doing it. Hopefully we'll get there somewhere. No, but this is already going way beyond that. I don't quite get it. How is that possible? So in that case, this would have been what? So you got 1 and 1 over there. This is like a0, this is -1. This was 0, this was 1 2. Okay, so just keep on going. It's like 1 plus 1 plus 1. So this would be 12. Fine. So a12 is really just what? 2 2 is like 3 3. Yeah, makes sense. The a10 thing is actually 1 4 4 in this case. Fine, and that's what we want. Next question. 16th. Okay, there are 11 seats in a row. 5 people are to be seated. Find number of seating arrangements if the central seat is kept vacant, and if for every, okay, fine. First one, 11 seats in a row. 5 people are to be seated. Number of seats. Okay, if central seat is to be kept vacant, so just remove the central seat altogether, right? Yes, now there are like 10 seats in a row, and 5 people are to be seated. That's the thing. Just wanna permute this. Exactly, it's like it's 10p5. Sure, that's just how it is, right? Yeah. So first guy can is like 10. Yeah, that's just the thing. So 10p5, which is like 10 times 9 times 8 times 7 times 1 2 3 4 6. That's the thing, right? That's only the first part actually. Yeah, central system kept vacant is just a thing, which is it just happens to be. Who cares? Why I won't actually calculate this. The next one is for every pair of seats symmetric with respect to the central seat, one seat is vacant. Okay, one seat is vacant. Fine. So you actually have to choose in that case, right? Yeah. So the central seat, is it vacant or not? Oh, it's and fine. So do we have to apply both at the same time? I guess yeah, the central one has to be vacant, it seems. And it's like only exactly 5 people, so oh fine. It's pretty awesome. So just 5 factorial ways of doing that, and then 2 power 5, because yeah, that should be the thing. So just 5 factorial times 2 power 5, which again I won't calculate. Why should I? And the thing is, it's exactly 5, so yeah. And that's assuming that central seat is actually not occupied. What if it is? Then you also need an extra one. So if it is occupied, then it's only 4 people. So it's like 5p4 basically, times 2 power 4. And the thing is, like 5p4 is also 5 factorial. So awesome. It's 5 factorial times 2 power 4. Yep. 17th. Take a convex octagon in which no 2 diagonals are parallel and no 3 are concurrent inside polygon. Okay. Find number of intersection points lying inside the polygon of the diagonals. Wait, what? Convex octagon in which no 2 diagonals are parallel. No 3
Hello?
are concurrent. Kind of weird. Inside the polygon. Okay. Of the diagonals, you want the intersection points. Hey, so like it's only diagonals. What's the number of? It's almost like the last one, except you just don't know what the number of lines are. Exactly. So it's a convex octagon. You got 8 of these guys. That's pretty easy. Just 7 plus 6 plus 5 plus. Yeah, that should be the thing. So for each diagonal, okay, let's just say that each diagonal is made up of 2 coins. It's kind of weird. For each connection, you put a coin in there. Does that actually make sense? I don't know. But that's the thing. 7 plus 6 plus 5 till 1. So just 8 times 7 upon 2, which has to be like. We want this to be in general way, shouldn't it be the thing? Yeah. So if there's like n points, then it's just n times n minus 1 upon 2, right? Okay. That's the number of things you have. Okay, and what's the number of regions? So we already got the formula before. It's 1 plus n plus 1 c2. So it's now it's going to be like 1 plus, instead of n, just put n times n minus 1 upon 2, right? Right? So it's like 1 plus, yeah, put that over there, and this plus 1. Okay, it's n times n minus 1 upon 2 plus 1 c2. This is weird. It's like this thing, n plus So 1 plus n times n minus 1 upon 2, and then oh, this plus 1 of course, and that times of n times minus 1, that thing upon 2, and all of that upon 2. Wow, weird. This is like n minus with, okay, yeah, this is nc2. So you know what, I like this thing, 1 plus nc2 plus 1 and all of that c2. Yeah, that's our formula. In this case, n is going to be what, 8, right? Of course it's nc2. From these 8 you just want to choose 2, except if you choose, oh no, it's number of connections, not number of diagonals. Shit, number of diagonals would be different, of course. So you don't want the side, these are the number of connections, which includes the side as well. So what you want to do is subtract from that number of sides, which is just 8, and in general it will be just n, right? Okay, that's the correct formula now. Awesome. Okay, if I just want to do this like this, n times of that minus was like minus 3 on 2. You just put that over there, right? Who cares, just move on. Right, and in our case this is going to be like what, 1 plus, so 8c2, which is 8 times 7 upon 2 is like 4 times 7, which is just 28. Am I right or am I right? 28 minus 8, that's just 22 plus 1 is 21, 21 c2, which is 21 times 20 upon 2 is like 210, 210 plus 1, that's also 211. Nice. So that's if n is equal to 8. Okay, next question. 18th. 18th is how many hexagons can be constructed by joining the vertex of a 15-sided polygon if none of the sides of the hexagon is also side of the 15 gon. None of the sides of the hexagon is also the side of, okay, and you want how many hexagons can be constructed, or like how many types of hexagon. Okay, yeah, how many hexagons. So that 15 gon is fixed on your paper, and then you want the hexagons. Exactly. Okay, so you can only get diagonals as the sides. Okay, it doesn't even matter if it's concave or convex, right? Yeah, because we only care about the connections, not, yeah, that should be the thing. That should be the thing. So you start off at one of the sides for which, okay, that's actually stupid. We just go with, this is kind of weird, isn't it? Yeah, it is weird actually. Can the sides intersect? Well, no, that would not be a hexagon. Oh no, this is not going good. Can be constructed. It depends, right? If it's a concave or convex, of what is happening. Yeah, I don't know how to answer this. Doesn't it actually depend on if it's concave or convex? I guess it does. It actually does depend. Because, yeah, I mean, think about like degenerate hexagons and stuff like that. That could be a problem. And we have not accounted for that. Fine, let's just go with the basic case. So if this 15-sided figure is actually concave and regular, yeah, for all we know it could be regular, right? Assume it's regular, and then we can somehow try to solve it. Alright, so if it's regular and you want to get how many hexagons can be constructed, we start off at one of the points, and then so you just get like this shape of the thing. Each shape will be different, I suppose. Not actually. Yeah, that's a problem. There's a problem with that. We can't just think of it as a journey, can we? Just tracing the hexagon's path. No. Because then the starting point could have been anything. Then there are going to be repetitions. Oh yeah. There will be repetitions like that. So think about it. Every hexagon that you will draw, in how many ways could that have been drawn if you choose the starting point with something else? So all of the vertices, you could have chosen them as the starting points, and then through some instructions you could have drawn that. So actually, right, that could have been drawn in 6 ways. So whatever number of ways you'll get, you have to divide that by 6. Right, so you're overcounting by 6 ways, aren't you? I guess that's the thing. Okay, then we'll just start. So we'll just think about what happens if we're gonna start and end at a certain point. Right, and we'll just divide by 6. So that will be this times number of points of this guy. Okay, 15 upon 6. So this 15 upon 6 times. So if you start at one vertex and then you keep going to other vertices, right? Actually number them or something like that. So I just say that starting vertex is 1, then you can go to something else and then something else and something else and then keep going. Okay, so you're gonna choose. Oh, and also it should not be side, so there should be a gap, right? So if you got places like this 1 2 3 4 to 15, you already occupied this one, then yeah, you don't want to occupy this, right? You can occupy this and stuff. Fine. So you got 3 till 15, I guess, which is 13 places. So these 13 places you want to occupy in a way such that, and how many are remaining? 5. So from these 13 places, in these 30 places you want to insert 5 such that no two are adjacent. So the 8 not selected ones, put them and then create 9 places and then insert 5. Exactly, it's just 9c4. For each of this, it's going to be 9c4 ways. Isn't that right? This is weird. Very weird, actually. That is 9, right? It's just 8 over there. God. Wait, let's start again. This was 13 places. 5 of them are already occupied. 8 are remaining. 8 plus 1 is 9. 9c. It's not 5, it's 4. You have to occupy 4 places. So 13 places, 4 are occupied. And then there are like 9 places that are remaining. So it should be 10 over here, because you'll create 10 such. Exactly. That should be the thing. Okay. So it's 15 upon 6 times 10c4. I hope this is correct. I really hope this is correct. Let's see if this is actually an integer or not. So this is 5, this thing is 2. 5 upon 2 times 10, 9, 8, 7, 4, 3, 2. Let's do that, cancel. There's 3 over there. Oh yeah, it's actually an integer. Awesome. It's progressive at least. So this times of 5 times 5. Sure. Which is like 105 times 5, which is 525. Next question. Next, 19th. 3 so okay, there are 5 distribution pair of gloves to be given to 5 persons. Each person must get a left glove and a right glove, and number of distributions that no person gets a proper pair. Okay, I get it. So first you just want to think about the left hands, right? So 5 factorial ways of giving the left hand gloves to these people, and then for the right hand gloves it's just leave 5. Exactly. So the fifth arrangement. So the recursion formula for the arrangement, that was just uh, dn is equal to n minus 1, I think. Yeah, right, like n minus 1 people. For switching it was n minus 1 people, and you will give it to exactly. Or you could give them the cap and then not take their cap, so you take someone else's cap, or take someone else's cap and then not give the cap to that guy. Right, and that's just dn minus 2 plus dn minus 1. Awesome, that was the thing, right? So let's just start. What's d1? There's no way you can actually derange with one person. What's d2? There's only one way. What's d3? There's two ways to do that, right? Yeah, I know, because I've memorized that. It's just we just know it's two ways because I've done that 1,000 times and now I know it. Okay, let's start. What's d4? d4 will be 3 times 2 plus 1. Yes, d5 is 4 times 11, 24. Is that right? It's got to be right, yeah. And what do you want? d5, exactly. Just 5 factorial times 44. That's our answer. I won't calculate this. Definitely not. Actually, it's not that hard to calculate. Just do this anyway. 5, 4, 3, 2, 1. This thing is like what? 220 times 4 times 2 is 3. Okay, guess what? 4 times 2 is 8. So 3. This is like 660 times 8, which is 0. It's 48. 8, 4 carried on 8. 48, which is 52. Yes. So it's just 5280. And minus, we'll just put that as d5. Next question, 20. 6 distinguishable marbles are to be distributed into 3 distinguishable boxes. Find the number of distributions so that no box is empty. No box is empty, okay. If this was indistinguishable marbles, we know how to do it. It's just the star bar theorem, right? But now that these are actually distinguishable boxes, this becomes much harder actually. So okay, let's start like this. Find number of ways to do it regardless of if the boxes are empty or not, minus if one box is empty. Or like, okay, that's gonna take a lot of time, right? So like at least one box is empty. That's actually stupid, because then you will go like 2 boxes are empty and oh, okay, there's only 3 boxes, so this is usually not that hard. So just 1 box is empty, or like at least 1 box is empty. Then for like 2 boxes are at least 2 boxes are empty, and then 3 boxes are empty. That's the number of ways, exactly. Okay, let's just start. So for all these 6, isn't there a better way of doing it? So at least 1. Okay, we'll just have to do it like this. There's no escaping it. Yeah, you just have to do it like that. Okay, so for each marble, how many choices do you have? You can, oh, and you have to necessarily put the marble into some box, right? Exactly. Okay, so you have 3 choices for each marble, it seems, right? Yeah, so just 3 power 6. Okay, minus, so if at least 1 box is empty, so this contains the choices where, wait, yes, it's not possible that all 3 boxes would be empty. Fine. Okay, minus, so if at least 1 box is empty, right? So let's just say the first one is empty. Oh, this is gonna be hard, isn't it? We'll be overcounting and stuff. Yeah, how many times would we have actually overcounted that? So the first box is empty, the second box is empty, then the third box is empty, right? And we'll add the first box and second box is empty. Exactly. So it's still okay. Inclusion exclusion, it still work. It still works. Oh god, this is weird. Yeah, this is actually very weird. But okay, believe on it and just keep going. Okay, so minus, we break one rule like that. Okay, so just at least one box is empty, or like exactly one box is empty. That could also work. This is weird, man. I don't believe in inclusion and exclusion anymore. That is pathetic. I mean, now I don't understand why is this gonna work, huh? Okay, let's actually try it out. So, number of ways in which the first box could be empty, that would be just, yeah, it's gonna have two choices, like 2 power 6. Okay, then subtract from that. So now what do we have remaining? It's just number of ways that we arrange this such that the first box is not empty, second box could be empty, third box could be empty. Right, cool. And subtract from that 2 power, so you combine this, so plus 2 power 6. So that's number of ways that the second box could be empty. Then you have to add the ways in which like the first two boxes are empty together, because then that's going to be either the first box is empty or the, yeah, I mean we are overcounting that, right? So it's not actually plus over this, it's negative, right? Then will be union. That makes sense. Sure, makes sense. Cool. So yes, actually we can believe in inclusion exclusion, fine. Both boxes are empty, there's only one way that you would put this, that's just 1 power 6 or something like that. Okay, this is kind of weird. Okay, then subtract 2 power 6 once again, because what if the third box is empty, and then you will have to do -1 for these two combined, and then the -1 again for these two combined. Is that making sense? So yeah, believe in inclusion and exclusion. So the usual way of doing this would just be like -3 times 2 power 6. That's the number of ways you can have at least one box empty. That's probably not the way you should be saying. It should be like 2 power 6 plus 2 power 6 plus 2 power 6, which is first box is empty, second box is empty, third box is empty, then plus first box and second box is empty necessarily, right? That's 1. Then once again 1 1 1 for second and third, then third and first. That's the way to do it. And right, so the wording matters, otherwise you will get confused. Fine. Yep, that's how it should be. So then calculate it. What's it going to be? You take a 3 common, it's just 3 power 5 minus 2 power 6 plus 1. So what's 3 power 5? Oh god, 3 power 4 is like, okay, it's 243, it seems. 81 times 3, yeah. Okay, minus 2 power 6, which is 64 plus 1. This is 244 minus 64, which is 18, 0. Sure. 540. That's it. 20 questions done. So I'll see you guys next video. Bye.